Alright, today we are going to focus on a little bit more of dealing with atomic structure, talk about the quantum model. This is just a reminder, if you haven't taken the time to read your book, it may not be a bad idea because you just want to make sure that you can understand this heady stuff that we're going to take to another level. Alright, before we get into the new quantum model, we got to talk about atomic history, a little review. 400 BC, Democritus coined the term atom. 1808, Dalton came up with his atomic theory. 1897, Thomson discovers the electron, which gives us the plum pudding model. 1911, Rutherford discovers the nucleus. We still don't know where the electrons are. 1913, the Bohr model gives us orbits, right? 2D orbits around the nucleus. But what we were still looking for is detail about where the electrons were around the nucleus, and the quantum mechanical model answered that for us. Alright, so a few more famous scientists. We've mentioned a few of these, but just as a review, we've got to talk about de Broglie, and we're going to talk about had matter could have wave-like properties, Schrodinger, and Heisenberg. And we've mentioned them before, but they're the big three when we get to the quantum mechanical model. De Broglie, we've already talked about. His big contribution is that he suggested that matter and the electron have both wave-like and particle-like characteristics. Einstein said, let's treat light like a particle, and de Broglie said, okay, sometimes we can treat matter and electrons as waves. So it's there. Again, here was his equation, the de Broglie equation that we saw a couple sections earlier. Now with quantum mechanics, this is going to take us a little bit further here, and I'm just giving you the basics. We don't have to really know too far in depth. But Schrodinger and de Broglie thought that an electron was similar to a standing wave. Okay, and each node, or dots, and that things must be a whole number or half wavelengths to avoid interference. Okay, so that they had to completely interact and get to the whole or half number in order to avoid complete interference with some of the math. Now with quantum mechanics, again, some of the ways they got there, only certain circular orbits have a circumference in which half the wavelengths will fit. And an electron must only be at certain distances from the nucleus or else there will be interference. And big take-home message is the idea that if you see this wave, it comes out to be equal. Okay, this one comes out to be equal, and this one is a mismatch. Okay, so there were numbers that did not work, and that's really what I need you to get to understand, is that 4 1/3 does not work. 5 works, and 4 works for these energy levels. Now the Schrodinger equation, here's the ugly version that I didn't even show you last year. This little pickaxe thing is what's called a wave function, and that's where we get this whole 3D position. I'm not going to ask you to do any math, I just show it to you so that you have an understanding and that you've seen it. What's called the operator is a set of mathematical instructions that produces the total energy. Again, you don't have to know the why, I'm just showing it to you so that you've seen it. Many solutions are found to the equation, but each includes a position for each amount of energy. And again, it's this whole idea that there's only certain numbers that solve it that is really the big take-home message in this scenario. Excuse me. Now again, we've seen this before. Bohr assumed quantization as fact and attempted to explain it with his atomic model. Schrodinger provided the mathematical evidence and support. So this was a pretty big deal at the time. Alright, Heisenberg uncertainty principle. Here's his ugly math. Again, I'm not going to make you do any math with it, I'm just showing it to you. Remember, he said we cannot know the exact position and momentum or motion of an electron at the same time. Delta X is what's called the uncertainty. This is our uncertainty in momentum. Here the M is standing for momentum and not mass. And as more is known about the position, less is known about the momentum. So I just try to remember that they're both of the uncertainties are inversely proportional. And that's really what I want you to know. I'm not going to say, what is the Heisenberg uncertainty principle equation? I just want you to have seen it so you can get some higher order understanding of what it means. Uncertainty is h over 4 pi. This is just that greater sign. Again, I'm not going to get you to understand too much with it. Okay, meaning of a wave function. Wave function itself does not have concrete meaning. Don't you love when you see that? But what it means is that the square of the wave function represents the probability of finding an electron at a certain point. And it's easily represented as a probability distribution, where the deepness of the color indicates the probability. And so this is where you have a density map where the probability would be in this darker area, and we can calculate probability of finding an electron of certain distances from the nucleus in the 1s orbital. Okay, and then obviously the further, here's our high probability, and that probability gets less and less and less and less as we get further away. Okay, so it's really just a lot of statistics to figure out where electrons are. Now, our meaning of the wave function, if we take this and we put it on an axis, the space around the nucleus is broken into shells. That's how we do it because it's what we understand the most. When the total probability for each shell is summed up, the probability of finding the electron is greatest near the nucleus, and the volume of the shell will increase. And so, just a couple of other ways that we look at each thing. Okay, so take-home message. Our orbital is our 3D area around a nucleus that has a high probability of containing an electron. De Broglie, Schrodinger, and Heisenberg did a whole lot of math, you don't have to know the details, to provide us with an area or orbital where there is a high probability of where an electron may be located. Okay? Alright, moving on, we got to talk about quantum numbers, and I think we're just going to get through quantum numbers and orbital shapes and energies. We're going to do spin and Pauli's principle a little bit later. Alright, if you remember from last year, quantum numbers specify the properties of atomic orbitals and of electrons in those orbitals. I think of it as the electron's address. Okay, it's just what sticks in my head. First three numbers come from the Schrodinger equation, and they describe the main energy level, which is the first, the shape, which is the second, and the orientation, which is the third. The fourth one is going to describe the spin state of an electron. Okay, first one is going to be the first quantum number. Alright, and the first quantum number is also the principal quantum number. And principal quantum number is abbreviated with the letter N. It's probably the easiest one for us to remember from last year. It's the main energy level or shell occupied by an electron. Values are all positive integers, 1, 2, 3, etc., etc. And as n increases, a few things happen. Number one, the size of the orbital gets larger. Oops, back up here. The size of the orbital gets larger. Okay, as n increases, a few things happen. Number one, the size As n increases, a few things happen. Number one, the size of the orbital gets larger, the electron has higher energy, and the average distance from the nucleus increases. Okay. Now, again, this just shows us here that there are different separations between the energy levels, but they're whole numbers and they're not equal distance apart from each other. Okay, again, if you think about it, purple light has the highest energy, so making a drop from 6 to 1, the difference would be purple light. Then you've got red, green, yellow, and red, which all have decreasing amounts of energy. It's that whole inverse relationship we saw earlier. But they are fixed amounts. Let's say second quantum number is the angular momentum quantum number. It's abbreviated by lowercase l, and it indicates the shape of the orbital. Alright, the number of possible shapes for an energy level is equal to n, and the possible values are all positive integers less than or equal to n minus 1. So, for the second quantum number, our s orbitals are spherical. They all have an L value of L equals 0, and they first occur at n equals 1, and they are spherically shaped, which we remember, again, you have increasing size as you go from 1s to 2s to, put that up there, 3s. Okay, for the second quantum number for p orbitals, there are 3 of them. They're dumbbell shaped, and they all have an L equals 1 value, because that second quantum number just tells us the shape of them. There's 3 because you have one on the x-axis, one on the z-axis, and one on, wow, let me try to get that right here. One on the x-axis, one on the y-axis, and one on the z-axis. When you put all 3 of them together, you get this big kind of conglomerate. And what will happen is that the first occur at n equals 2, and for n greater than 2, the shape is the same, but the size increases. So if this one is 1p, 2p would be a little bit bigger than that, 3p would be a little bit bigger than that, etc., etc. Okay, now with the d orbitals, they're mostly cloverleaf, and the L is equal to 2. They first occur at the third energy level, and we'll do our electron notation stuff. that will kind of bring all this back as well. But they mostly have cloverleaf with the exception of this last one that kind of has the funky, inner tube in the middle. And same thing, n greater than 3, same shape but larger size. So if this is the 3D orbitals, the 4Ds would be kind of the same shape but just a little bit bigger. And then the Fs. There are 7 types. They have all kinds of variations. Excuse me, L equals 3. They start beginning at n equals 4. And again, if we had the 5F, it would just extend beyond all these balloons for every single one in each different direction. And as you can see, they just get a little bit more complicated. Alright, anyway. That's the second quantum number. Other shapes could exist in the energy levels as long as they follow the rules. We could potentially have a G that starts in number 5 with 9 orbitals. We could have an H, would have L equals 5, starts in 6 with 11 orbitals, etc. But we just haven't found anything that to be the case, so we don't have any of them yet. This is just a summary that reminds us at n equals 1, we just have a 1s. At n equals 2, we're going to have a 2s and a 2p. N equals 3, we've got a 3s, a 3p, a 3d. And then in the 4s we get 4s, 4p, 4d, and 4f. And we'll talk about the orders a little bit later. Okay, the third quantum number is going to tell us it's the magnetic quantum number. It indicates the orientation of an orbital around a nucleus. They have values from +1 to -1, and it tells us which of the orbitals where there's more than one option does that electron stay in, and there's 2 electrons per orbital. Total number of orbitals is equal to n squared for an energy level. And this is just another one, but total number of possible magnetic quantum number values for a certain subshell is 2 times the angular momentum number plus 1, but I don't know that we really remember that very often. Here's just shows you all the options. For the P's, remember the P's would be -1, 0, and +1 because you've got an X, a Y, and a Z option. And then the D's go from -2 to +2. The F's go from -3 to 3 with 1, 2, 3, 4, 5 total options for all of the D's. 1, 2, 3, 4, 5. And 1, 2, 3, 4, 5, 6, 7 total options for the F's. Okay, and then this just summarizes this chart again in terms of number of orbitals, the total number of orbitals in that level. Just as a reminder, 4 squared is equal to 16, 3 squared is equal to 9, and 2 squared is equal to 4, which is just a quick reminder of where those come from. And last but not least, we have the spin quantum number. It just indicates the spin state. There's only 2 possible directions for these, and 2 possible values are +1/2 and -1/2. That's going to be one thing that's different this year, is you actually have to assign quantum numbers to different orbitals, and so we need to keep that in mind. And the paired electrons have to have opposite spins, which is going to satisfy most of the rules for electron configurations. And then if the maximum number of orbitals in an energy level is n squared, we multiply that by 2, that's the total number of electrons that are available in an energy level. Okay, I hope that helps. See you next time.